So far, we've already covered how to handle a general simplex problem where you have greater than or equal to constraints. But what we have not covered is what do you do if the problem isn't asking for a max? What if it's asking for a min? Well, the solution to this is actually quite simple, and it just hinges upon one very simple idea. Where if I, for example, gave you the graph of negative x squared. There we go. There's one of the negative sign in there. Now, if that graph, if you just kind of imagined it, that would be a graph opening down, parabola. This thing would have a maximum. Now, what if instead I gave you the graph of, and you had some process that worked for finding maximums, but if I changed it so it was x squared, and now whatever process you have only found minimums, not maximums, what would you do? Well, you would say, well, this graph wouldn't work because this is asking for a min, not a max. Well, what if we reflected it? What if we just took your whole function and multiplied by a negative? Then that would turn this graph here into this graph here, and now you could use your process, but you would have to know that your value is the opposite of what it should be. So, for example, what if instead of just being negative x squared, it was negative x squared plus 2? Well, then what would that mean is we would be opening down, we'd be shifted up 2, so our graph would look something like this. And if we had reflected it, well, then it would be like this. So the idea would be very simple. If your process only found maximums, but you had your problem written as a minimum, we know our answer should be negative 2, but when we used our process, if we reflect the graph, if we just multiply the whole thing by a negative, it would make it into a positive 2. So we just know our answer is the opposite of whatever it says. So if our process told us the answer was 7, then we know it's negative 7, that kind of thing. Okay, so what we're going to do here, if you follow that, all we're going to do here is just reflect this. So instead of being a minimum, what we're going to do is multiply everything by a negative 1, everything by a negative 1, and now, instead of asking for a min, the problem now asks for a max. But this is kind of weird. We don't like having the negative c there, so what a general practice is instead of writing it as negative c the entire time, we'll just call it a p because it's p stands for profit, and that's you maximize profit. We just have to remember at the end that whatever our value for p is, switch it back to the opposite. So if we get the value of 17, then our answer is negative 17, or vice versa. Now, you actually couldn't ever have the value of 17 because remember we have the restriction that all of our variables must be greater than or equal to 0. So that is x, y, and p. But I hope you get what I'm saying. So the process, what makes this problem different than every other problem so far? It asks for a minimum. So what do? You just take your entire function, multiply the whole thing by a negative 1, which just flips the graph. We then, instead of writing c, we'll write p, but then what that does for us is it just makes it so we treat the problem like normal. So now you do the problem exactly like you had done before. So treat this now as a practice problem, and up until reading your final answer. So I would highly recommend pause the video, give it a shot, and here we go. Okay, so step 1, take your objective function, rewrite it so p has a positive leading coefficient. So that's going to give us 6x plus 6y plus p equals 0. All right, there's our objective. Now all of our constraints. This would be x plus 2y greater than or equal to, so we need to bring that down, so that's going to be a minus. Q equals 20. And then for the second one, that's going to be 2x plus y minus r equals 20. And if you want to visualize what's going on, I did give you the graph, and what you'll see is when you shade it, it all shades up. So you'll see we actually only have one corner point in this whole graph. It's right there. So when we're starting at 0, 0, we're going to say which way we're going to walk, in the x direction or the y direction. And because of the symmetry of the graphs, to me it looks like there'll be a tie. We'll see it when we look in the matrix. But the idea is you also can know we're not going to be our shaded region. We're going to go ahead and we're going to pivot either on the green or the red, and we should still have a negative on our answer because it's not shaded. So then we're going to travel, depending on our direction, we're either going to travel up here or down here to get to our pivot, or we might travel up on the axes to get to the shaded region on the intercepts. But whatever the case, it's going to take two pivots to get to our shaded region. We know our first pivot's not going to get us there, so we're still going to have negative solutions. Okay, so here we go. We've got our matrix. We got our values to substitute in our matrix. We have our objective function. We're ready to rock. Let's do this. So the matrix will look like we've got x, y, q, r, p equal sign. Our first equation is going to be a 1, 2, negative 1, 0, 0, 20. Our second equation will be 2, 1, 0, negative 1, 0, whoops, 20. And our third equation, our objective equation, is going to be 6, 6, 0, 0, 1, 0. And sometimes students kind of lose sight of what we're doing, and they say, "Oh, but there's no negatives in the objective equation, which means we're already maximized." Well, no, we're not in our solution region. Remember, we're standing at 0, 0, so therefore this doesn't matter. The answer is a gibberish answer anyway. It doesn't satisfy the other equations. So we start off by just saying, okay, which of these values gives us a negative answer? So x equals 0, y equals 0, negative q equals 20. There's a negative. And negative r equals 20. There's a negative. Okay. And we kind of knew that those would both be starred because they're both greater than or equal to, which means they're both messing us up and they're shading up. So therefore, they're both going to get stars. So which one do we pick? Either one. It doesn't matter. It's just like if you had a tie in your objective, you've got a tie here, pick a starred row and start going. So I'll do the top row. Row 1. Look for the largest positive number. That's a 2, so that'll be our pivot column. Yes, you cannot use the equal sign because you don't pivot in there, so we're looking for a pivot column. Okay, now looking for our ratio. 20 divided by 2 would be 10, or 20 divided by 1, which would be 20. Well, 20 divided by 2, 10. There's our pivot right there. That's the smallest ratio. So we're going to walk until we reach the y-axis. So that answers that question. We are going up. All right. So your row operators would be, let's see, we need to do negative row 1 plus 2 row 2's to make a new row 2. And then we need to do negative 3 row 1's plus row 3 to make a new row 3. All right, I have already put this into our little website. So we're going to pivot on that column. So then we're going to pivot on that selection. There we go. All right, so now you can see we have our new matrix. So let me pop this over to the side. I'm going to go ahead and copy it down, and I will start the video again once we are all done copying it. And something may have happened that might freak you out a little bit until you stop and think about it. You'll notice we have a negative 60 here. We're not supposed to have negative numbers there. We've never had negative numbers there. We're not allowed to have negative answers. But remember, p equals negative 60 doesn't really mean p equals negative 60 because it's the reflection. So that means our c would equal 60. So we actually expect to see a negative number there. We want a negative number there because that means after we reflect it back to our correct answer, it'll be positive, and that's okay. So don't let the negative freak you out. We're okay. So now let's read. Here we go. X equals 0, y, so that we're going to keep. Q equals 0, R we're going to keep, P we're going to keep. Okay, here we are. Now, we already said graphically we know we are not going to be our solution region, but let's verify. First row, 0, so let's see, 2y, 0 q's, R 0, 0 equals 20. So now I have y equals 10. We already knew that from the previous equation. We knew we would be there, but that's okay. It's a positive answer. Good to go. The second row, so 0x, 0y, 0q, negative 2r's equals 20, so r equals negative 10. It's negative answer. We need to walk towards that equation. And like I said, we already knew that. We're standing right here. our question is do we going to go to in the y-axis, or do we want to go in some kind of combination of the x and the y, some diagonal way to get there? Well, so let's look for the largest possible number, and you have to remember it's kind of we're reoriented. Our perspective is reoriented, so it is okay. These don't have the literal meaning of x and y anymore. Um, let's see here. So we are going to go 3. 3 is the largest positive number. There we go. All right. Now, ratios. 20 divided by 1 is 20, or 20 divided by 3. That one's smaller. I don't need to know what the number is. I just know 20 divided by 3 is less than 20 divided by 1. So, row operators. Negative row 2 plus 3 row 1s to make a new row 1. And then negative row 2 plus row 3 to make a new row 3. So there's our pivot, there's our row operators. Let's use the handy dandy little website because I'm all about that pivot on that selection, and there we are. So now I'm gonna copy down this matrix and let's take a look at it. So now we have our matrix, and what we're going to do now is rinse and repeat. We're going to check again. So x we keep, y we keep, q equals 0, r equals 0, p we keep, equals we keep. So now, and you can, if you have gotten good at this, you'll scan across and just say 3y equals 20. Don't really care what that number is, but I know it's positive. 3x equals 20. Don't really care what that number is, but I know it's positive. And those are my 2 rows, which means everything's positive, which means now standard simplex kicks in. We're back to standard simplex. And what does standard simplex say? Well, look in our bottom row, now that we're in our solution region, look in your objective and look for the largest negative value to pivot from. And look, they're all positive, which means we're done. We ended up, our first corner point happened to be the solution. So we're done. So I actually do care what these values are. Y equals 20 thirds and x equals 20 thirds. P equals negative 80. But remember, whoops, P isn't actually negative 80, right? Because we said P is really negative C. It's the reflection of our goal. So therefore, negative C, whoops, not 6, negative C equals negative 80. So therefore, C equals 80. So what is our answer? We have a min of 80 at 20 thirds, 20 thirds. All right, so thus concludes general simplex. What's the difference? Well, general simplex can handle any problem as long as your variables are greater than or equal to 0. So you've seen a problem that does minimization, you've seen a problem that does maximization, and the key to it is you've seen problems that have greater than or equal to in their objectives, in their constraints. That is the hardest part of the whole method. All right, we'll see you in the next section.